Hello, I am Dr. D.S. Kushan. This presentation describes my research proposal for a postdoctoral fellowship in aerospace engineering focusing on high-speed flow and thermal infrared studies for scramjet and rotating detonation engines. Let's dive in. The vision is to develop an experimental program that combines high-speed flow diagnostics with infrared thermography to understand cooling performance and unsteady flow physics in these engines. The emphasis is on using high-speed cameras and, where feasible, high-speed PIV together with IR imaging on scaled scramjet and RDE configurations tested in existing wind tunnels and propulsion rigs rather than full-scale engines. Scramjets and rotating detonation engines are leading candidates for future hypersonic and high-efficiency propulsion, but both face critical challenges. Scramjets must maintain stable combustion in supersonic flow while keeping vault temperatures within material limits through active cooling. RDEs promise higher thermodynamic efficiency but operate with rapidly rotating detonation waves that impose intense cyclic thermal and pressure loads on chamber walls. In both cases, cooling design and transient flow behavior are tightly coupled, and existing data on detailed thermal response is limited, especially at the time scales relevant to these engines. The core of this work is an integrated diagnostic suite. Infrared thermography will provide time-resolved vault temperature maps and cooling effectiveness on instrumented test sections. High-speed cameras will visualize shocks, jets, flame zones, and detonation fronts in scramjet-like and RDE-like configurations. Where optical access and seeding allow, high-speed PIV will deliver synchronized velocity fields in key regions, building on existing PIV and flow visualization capabilities in the department. Together, these link flow structures directly to thermal loading. The experiments focus on representative sections rather than full engines, making the program realistic within current facilities. For scramjets, scaled isolator combustor segments and cooled wall panels will be tested in existing aerodynamics and propulsion rigs with controlled inflow and optical access. Concepts like channel, film, or transpiration cooling will be compared by tracking vault temperature histories via IR and observing shock boundary layer and flame behavior with high-speed imaging. For RDEs, annular or single sector channels will be run in lab-scale rigs at suitable pressures and temperatures with high-speed imaging capturing detonation, wave structure, and frequency, and IR thermography quantifying associated vault temperature fluctuations. This program builds on existing subsonic and supersonic tunnels and propulsion test rigs at IIT Kharagpur, which already have optical access, flow visualization, and PIV capability. The proposal is to augment these with IR cameras and higher frame rate imaging PIV modules, rather than creating a new full-scale hypersonic facility. Over roughly 2 years, the work proceeds in 3 steps. First, develop and calibrate the diagnostics in simpler flows. Second, apply them to scramjet-like sections to quantify high cooling strategies and operating conditions affect flow and wall temperatures. Third, extend them to RDE-like channels to relate detonation wave characteristics to thermal loading patterns. Expected outputs include high-quality datasets for model validation, journal publications, and guidelines for improved cooling of high-speed propulsion components. In summary, this postdoctoral program uses infrared thermography, high-speed imaging, and high-speed PIV to connect high-speed flow physics with practical cooling design in scramjet and rotating detonation engines, RDEs. By working with scaled configurations in existing facilities, the plan is experimentally feasible yet addresses core questions in hypersonic and detonation-based propulsion. The long-term vision is to support more robust designs for future high-speed flight systems. Thank you. I would be glad to discuss any questions and potential collaborations.